So hi all, I'm Lesley, and today's topic is type erasure. I will talk about what type erasure is and also how to implement them in C++. About me, I'm a computer science and applied math undergraduate student at University of Colorado, and I am also an intern at SketchUp. And I'm a
SketchUp team come and support you here?
Yeah.
Oh, okay. All right.
And I'm a computer graphics person, so feel free to ask me about stuff like importance sampling. I'm aware of there are multiple people in this room are much better at graphics than me, but whatever. And about the talk, so in last CPPCon, I took a pre-conference course called STL from scratch from Arthur O'Dwyer, and he talked some like how to implementing type erasure technique to me. So some of my ideas from him, but all the error are mine. So I implement from scratch. So type erasure, like almost all terms in computer science, are severely overloaded with different meanings. So the first meaning is compilers erasing static type information before runtime. We will explain that later. The second meaning is in generic programming, programmers circumvent static type system to achieve dynamic polymorphism. But even with second meaning, different languages like C++ or Java will have different interpretation on what exactly is type erasure, but I think this is general point. Oh, well, this is a compiler explorer. I didn't connect to Wi-Fi, that's a problem. So the idea is basically the static type information.
Yeah, if you need it for the rest of your presentation, let's make sure you get connected.
Well, it's not important. So.
Oh, it's not important?
Just
this one slide.
Okay.
Yeah, the idea is the static type information get erased when compiler compiles. So I have two unrelated functions. They compile to exactly the same assembly. So that's a basic idea. Not our focus today, even though it's a fantastic topic. If you want to learn about compilers, then yeah, this is something you need to research on. And if you search Wikipedia what is type erasure, then this is what you get. However, we will talk about type erasure as a method to achieve dynamic polymorphism, because that's what C++ community usually call type erasure for. So I will talk about several type erasure techniques. There are others, but in C++ we have one is so-called C-style type erasure, which is basically a cast, and the other is virtual dispatch. The third one is structural typing, and that's what I will focus most of the time on. So so-called C-style type erasure is just a cast, so it's obviously very fast. You lost all the type information, static type information by doing a cast. Basically, you enter this type unsafe land, and the compiler can do whatever if you are doing stuff wrong. So it's not type safe. For example, here is a GLFW, which is a window library where you can append arbitrary data into the window called by this user pointer API. And notice the void star here. So when we pass in the pointer in, we pass it as a void star. And when we want to get back the user pointer, we get back the void star. So the usage in a typical application is something like that. For example, we have a class, and inside that class, we may set this window pointer to this pointer, which is that object itself. Of course, this is not the only possible workflow with this library, but that's just normally what C++ programmers do. And inside that class, we store window, but we also store other informations. And when we have a callback to handle, for example, keyboard input, we will just cast the window pointer back into its original type. In this case, it's totally zero overhead, or I should say zero cost, because we know at static, we know exactly the type of what our user pointer is, but we just want to circumvent the type system. Notice here is a cast, so we cast the information back to the original type, and then only after that we can use it. Now let's talk about inheritance. Inheritance is like computer science 101. Everyone started to do it in kindergarten. So here's a ray tracing example. So let's say in ray tracing we have different shapes, and we need to test. One thing is we need to test if we have a ray, if it intersects with that object or not. The second thing we want to test is giving it a bounding box, which is like a rough range of where that object is. That's used for optimization purpose. Also, we need a virtual destructor, because otherwise things just don't work. So we have 3 virtual functions, virtual destructor, the bounding box function, and the intersect function. Of course, we need to make client tidy happy. To be honest, I don't understand the purpose of those, but just make client tidy happy. And we can have a bunch of derived class that contains some data, contains arbitrary data, and then we implement those functions. And we can have different derived class with different data and implement those virtual functions in different ways. And this class is more interesting. So how many of you are at or watched the Matt Goldbold's path tracing in 3-way talk last year?
I watched it.
Yeah. Well, I would say his data-oriented approach doesn't work because of this. So why his approach don't use an accelerated data structure, but once we start using accelerated data structure, so our shapes become organized in a tree. In this case, we have 2 pointers point to the left and right side of the, and we also have a cache, bounding box cache. In this way, because our object is organized in a tree, it's really hard to separate different objects into different vectors, for example. So the only way seems to work is to use dynamic polymorphism. That's why I picked this example, because if it's animal and then just different animals stored in a vector, then you can think about better ways just using multiple vectors. So virtual dispatch in standard library. So PMR, memory resource, is the only thing I know. Standard library don't like inheritance. To be honest, I don't even know why memory resource is implemented with inheritance. Probably some people in here knows. Yeah?
Virtual polymorphic allocators are a big thing in game development, so you don't have to have a different allocator than your template type.
Yeah, I know, but why not implement it like stud function, but implement it in this way, with inheritance? That's the thing I don't understand. So there must be a reason. So virtual dispatch pro and cons. Pro, idiomatic, everyone can read that code, can write that code. Don't underestimate that. That's really important. because if you hire a C++ developer and then your code base is full of like template method programming, they will probably gone in the second day. And also, the technical advantage of virtual dispatch is called open recursion. So the open recursion is the idea where you, for example, you have a base class, it implements something, you have derived class, and you may or may not override that virtual function. And no other technique can have that degree of flexibility or code reviews. So that's probably the only advantage I can think about technically about virtual dispatch. Disadvantage, some parent hates virtual function. You should watch this talk. I will not say that's a really good reason, because there are a lot of influential folks talking about nonsense. So, but Sean Parent is definitely someone you need to listen to, but still listen to his reason, not believe him because of his status. So here is some real reason why virtual dispatch may consider be bad. One is it's intrusive. So every time you need to define base class and then your derived class inherits from base class, you cannot say like I define interface work for third-party types, for example. This may or may not be bad because on the good side, intrusiveness also means you cannot inadvertently implement an interface accidentally, like. Or like you have two classes have same master signature and they do totally different thing and they implement the same interface, stuff like that. Other bad things is reference semantics. Also, reference semantics means it's kind of coupled with dynamic allocation and explicit memory. Not absolutely. You can still allocate stuff in static storage or on the stack, but that becomes really inconvenient. So mostly people do is allocate every object onto the heap. Then that's expensive and also means you need to do some kind of management. Even unique pointer is not like just allocating on the stack. Virtual function cannot be inline, so yeah.
It can be inline.
If get devirtualized, but
yeah. I just argue for being a mortal wound instead of a murder.
People most likely die from because it's very rare to get something to be devirtualized.
Yeah.
Yeah, I would not trust those kind of stuff, to be honest. Like, why we use C++? Because we don't trust, like, our, for example, JIT compiler can magically do everything for us, transforming horrible programs into good ones. Okay, so the idea of structural typing, the definition I copied from Wikipedia is type compatibility and equivalence are determined by the type's actual structure or definition. So a lot of people in C++ community will call the same concept dark typing, but the two terms still have differences. So dark typing implies you defer the type checking until later. Like in a dynamic type language, you only check the type error at runtime, or in template, you check the error at instantiation time. And structured typing implies you check type error immediately. So that's a difference. So there was an idea of concept checking that never become a thing in C++, at least in C++ 20. But if concept checking is implemented, then we can see C++ templates have structural typing now, not dark typing. There are a lot of languages implemented similar ideas. For example, Go interfaces, TypeScript interface, OCaml row polymorphism. There are some related ideas, but it's intrusive. So as I said before, intrusiveness is not necessarily means bad. That's why those languages still implement in intrusive way, like Rust trait, for example, and also Haskell type classes with protocol. And also OCaml module signature are example of Other things are kind of like stud function, but every time you write a new function, you need to, like say it's from stud function, for example. It's implement a function interface instead of just write a function. So let's talk about terminology called affordance. Affordance is a terminology come from the UI world. It means a property or feature of an object which presents a prompt on what can be done with this object. So basically the behavior of that object. Because we care about behavior more than the actual data, at least in the cases I will talk about. That's why I will use this term. There are a bunch of talks that propose use structural typing instead of inheritance. Like this talk is like the evolved version of that. Inheritance is a base class of evil talk. And all of those talks kind of propose to use some library they wrote instead. So let's have an example of structural typing. So this is C++'s concept. As I said before, concepts don't implement concept tracking, but let's assume it is. Then we have a hitable concept that at the first we have a bounding box function, member function, and we say the return type is AABB. We also say the hitable must have intersects member function that takes a bunch of parameters. The return type will be this optional hit record. So it's like exactly as the previous virtual version, but then when we use concept, our types don't need to inherit from this concept, for example. Of course, concept only works for static stuff. If we want dynamic stuff, then there was a proposal about virtual concept, but that's never become a thing, and I don't think it will ever. Because runtime is a lot more complicated than compile time. Yeah, at compile time, it's at least for template meta programming, everything is like really pure. But at runtime, we care about value versus reference semantics. We care about ownership problem, who owns this memory. And we want optimizations, like small buffer optimizations. All of those ideas are not representable by the previous virtual concept idea. So if we want to really have something like virtual concept, then the proposal needs to answer those questions. So as we said before, shape have 3 virtual functions, and to here it's 3 affordance, which is destroying and getting the bounding box and intersect with array. There are a bunch of standard library types using structural typing. Stud any, stud function, stud shared pointer. So the first 2 are not surprising. The third one is type erased because of the allocator. So stud any, I want to do a little poll. How many of you used stud any in production? 1, 2, 3. Okay, yeah, so as we see, stud any is...
They do everything at compile time.
Stud any is kind of more specific, so not as useful as the other additions and like in C++17 or like stud function. So I will not talk about that. Especially stud any is not a safe replacement for void star. For example, in my previous user pointer example, if I use stud any, then I introduce overhead I don't want. Other thing is stud any is an owner versus void star are usually used as a non-owner. And basically, type safety cost plus stud any is not really type safe because it's type safe, but you still need to, every time you want to do something, you need any cast. That means, yeah. So stud any have several affordances. copy, move, destroying, and getting RTTI information. So copy and move are kind of optional, so they are kind of guarded by some Sphinx code. If your object don't implement copy or don't implement move, that's fine. That's why any can basically contains anything, because the only real requirement is destroying, which every object can destroy itself, and RTTI.
So any can contain a non-movable object? Or you say it must be movable?
I'm not sure about move, to be honest. I'm pretty sure it can contain non-copyable object because Sphinx guard.
Okay.
But yeah, I haven't checked move. Yeah, now let's talk about stud function. Because stud function is used more. And probably if I do a same poll, then more than half the people in this room use that thing before. So why we need stud function? Consider a distributed lambda in C++, which is basically a class with invocation operator param operator. So this thing is really simple. If I want to be really exact, I also need convert to function pointer conversion, but I omit that. This is lambda in most languages you've seen. So this lambda is very sad, yeah, because this lambda inherits from some base class and do some virtual dispatch. And the basic idea is those languages already perform type erasure for you. If you coded in Java-like language, you're probably seeing this function type on the wild. If you are coded in those functional language, all those languages have so-called proper function types, then this thing, basically the language handles this for you, but it's still the same. Because all those languages have the problem of we don't know the size of a function object or a closure. So the only way to do it is dynamic allocation. In C++, we don't want all of those, so we have stud function whenever we really want that dynamic polymorphism. Stud function supports several operations: copy, move, invoke, destroying, and RTTI. Now let's talk about something better than stud function, which is called unique function. So the only thing different from unique function, well, not the only thing, but one thing different from unique function from stud function is you can no longer copy unique function. And why? That is better. So consider this way: if your affordance is less, so you can do less things, then it can cover more types. In this particular case, because unique function do not need the underlying object to be copyable, we can pass move only type into that. And also unique function don't implement RTTI, and who care about that? So that's a case study I want to make today is implementing unique functions. So finally, some non-slideware code. Not exactly, I write that code for slides, for this talk, basically. So unique function version 1. We still implemented unique function with virtual dispatch, but because they're kind of doing the same thing, just we want to become non-intrusive. So we have a base class that defines all the polymorphic operations. Like we have a virtual destructor, and we also have this invoke operation that basically just forward all the arguments and to some underlying function and return something. Notice is we don't have move there, even though we said move is an affordance of the unique function, because we will see it later. So then we can implement the actual unique function storage. So this storage is a template that have a function wrapped in. And then for the, I think, yeah. So for the constructor, we just pass argument in, just like what, for example, your lambda capture in, and then construct a wrapped function object in it. And for the invoke function, it's the same process. We forward all the arguments into a wrapped function. And for people who are not familiar with like variety templates, forwarding references, start forward, and there are talks about that. Also, I have some really bad naming convention here. I call the arguments that passed into the invocation args, and I call the argument passed to a constructor a. That's a really bad naming convention because I can easily flip these two and this code still makes sense, but that's just what I use. So the constructor, as I said before, just forward arguments to construct the wrapped function object. And we have this invoke function do exactly forwarding to the underlying function. So our main unique function,
We have a question. Can you go back to the slide?
Yep.
I don't think that that's a forwarding reference there because your function is not a template function.
Oh, I see.
Okay, so you agree?
Yeah, I agree.
Okay. So that should be a template function?
Yeah.
Okay.
But the structure is a template though. Like that's where it picks up our structure.
Yeah, but the types become concrete at that point. And they're
Yeah.
no longer forwarding, that's not a forwarding reference outside the function call.
Yeah, and I think I made these mistakes over and over again in all these slides.
No big deal, let's add template in front of each one.
Yep. And this is the actual implementation of unique function. I don't show all the parts of the class because some parts are not that important. So first is our unique function class is specialized on the r-param args type. And the default class is left unimplemented. That way we can only use unique function in that syntax, just like std function.
Virtual function can't be a template function.
Yeah, and yeah, then we have this storage as a pointer. So now we can see why we don't need to define move as in our storage, because we use it as a pointer. We have some default or like empty constructors just doing nothing. And we have this constructor, this scary looking constructor. Well, stripping the spin is not that bad, but so we have this check to make sure our constructor is not too generic, because if we look back before, this func ref can sometimes be better in overloading resolution sense than, for example, a const ref or something. So sometimes it will take the job of a move constructor. That's why That's why I want to inflate some finite guard to say if I can use move constructor, then use move constructor instead of this function. Otherwise, I use this function. And we also have this implementation of operator param that basically if I have a function inside, underlying function inside our unique function, we invoke it. Otherwise, we throw some exception. By the way, I hate exception. I think it's the biggest mistake of C++. I know. Well, I know.
What else would you do in that case?
Panic, just. Well, to be serious, there are two kinds of errors. One is you cannot recover. That's when you should just crash the program or handle it at some callback. Or the other cases is recoverable. Then you should handle it with control flow, not exception. So exception, I don't like exception because of that. But that's the behavior of stud function, so I will implement that exactly this way. Some not so important operations, including swap, operation bool, operator bool, and also a bunch of comparison to null pointer. I omit the deduction guide because one, it's not useful for our discussion. Two, there are two deduction guides for stud function. The first one is really trivial. The second one means 100 lines of macros. So I don't want to put it on the slide, and I don't want to write it. Basically, I forgot the detail, but I remember standard library probably missed some type traits I want, so that's why I need to write it myself, basically. And unique function version 2. So I guess I forgot to say that before. So stud function have this constantness bug. When I give stud function a mutable function object, and I say, hey, this is a const, we can still call that stud function. As a result, the underlying function object can be mutated. That's not the const correctness we want. Even though stud function is implemented in this way, and our unique function so far is implemented in this way. So our previous version is like that. New version, we just add a new base class and duplicate all the code for the previous unique function class. Yeah, it's nothing more, just a duplication. And we have two overloads. One is a non-const overload of the unique function. That the only difference is in that invocation, our function signature don't have const anymore. So we can no longer call a non-const version of unique function when we make it const. So a const non-const version of unique function can do nothing, basically. And we just forward stuff into the base function in the base type and let the base type do stuff. I think this kind of thing is the normal technique when you have two different specializations and they share most of the code is inheritance. I also define this function. I don't remember if this is in proposal or not, but I think it's nice to implicit convert a non-const version of unique function into a const version, so I write this. And the const version is also really similar, except at here we have a const because it's a const overload. And at our operator param, we have our const back. So we can call a const unique function. We have yet another finite check to check if we can invoke this function if it is const. Or invoke the underlying function. So if underlying function is a const reference, can we still invoke it? why not use that is invocable here? Maybe I should. Yeah. Now it's actually what we want. So those kind of two yield form code will no longer compile. The first one, we give a mutable lambda into a const version of unique function. The second one is we have a const version of non-const version of unique function, but make it const, and then we can no longer call it. So our virtual dispatch implementation is pretty simple. Everything is still on the heap. No small buffer optimization. Still, well, trying to murder inlining. Now, unique function version 3. We want to put more data in the stack. But first, there are no way to put more data in the stack if we use inheritance. So we need to create our own vtable. There's some ugly code there waiting for you. And if you think vtable is mysterious, it's really just a bunch of function pointers. Then we have this behaviors class that just store function pointers of the polymorphic behaviors we want. By the way, C function pointer syntax is just horrible, but I guess most people are too love this language to admit it. And we have this kind of helper factory function to create the behaviors. And I use the C++20 designated initializer, because why not? I love this feature. And we had cast before. Now in our C-style type erasure stuff, and now we also need to do this kind of cast ourselves to cast the storage, because it's a void star, back into the original type we want. This plus is just a trick to cast lambda into a function pointer, because lambda is an object. You cannot do arithmetics on objects, but function pointer are kind of pointers, so you can add plus to pointer. That's why you can use this trick to force lambda become a pointer. And our new storage is just a void star. And also this helper function to construct our new structure by calling the global new. Of course, you can use an allocator, but that will make this implementation more complicated. Also, stud function and unique function proposal all don't do allocators anymore. I store data in void star. Notice the whole storage is no longer a template. The template is behavior. At behavior, we need to specify its return type, what argument it take. And this create function, we even need more templates to specify what the actual type is. But our whole storage is no longer a template because it's just a dumb pointer. So now we store our vtable explicitly in our unique function class. Well, JavaScript stuff. All of them are amazing and broken at the same time. Yeah. Then inside the constructor, we just call those helpers to construct the storage and also the vtable for us. And then to invoke the actual function, we need to call the underlying function pointer inside behavior. So since we no longer use a unique pointer, we can't use a unique pointer for void star. So the only way to do it is handle all the ownership stuff ourselves. So this helper basically says, if the behaviors exist, if the vtable exists, then we destroy the storage by calling that destroy pointer. So that's basically the exactly same purpose as virtual destructor of those polymorphic types. Also, we need to write our own copy. Not copy, we just delete copy because it's a unique function. And we need to write our own move. So state exchange is a great idiom to implement move. I used to use swap because Pioneer's book used swap, but for swap you may kind of make the lifetime of the move from object too long. That's why I use exchange now. Also, there's ampersand in move and copy assignment. The idea is this is not normal, but the idea is like we should not allow any assignment to our value reference. To not reference, just to any R value. That's why we add this ampersand. And there's a paper proposed to make this the default behavior. Unique function version 4. So we add our own vtable now, but everything is still on the heap. Now we need to add small buffer optimization to make stuff actually on the stack. So our current storage is a void star, which points to some heap memory. And now it's become a union that can be either a large. If it's large enough, then it will be on the heap on with void star. If the underlying function object is small enough, then we will store it inside a byte array. And I have this helper meta function to decide if our underlying function object can fit this unique function storage, the small storage or not. Now our in-place function also need to change. For large, we still do the same thing, but for small buffer, we use placement new to construct into that array. And similarly, our operations need to dispatch on if the underlying function object is big or small. If it is big, we do the normal stuff. If it's small, then for invocation, we need to find the storage differently because it's no longer a point to some storage. It's an array of storage themselves. For the destroy case, then we just call destruct directly, not calling delete. So are we done with this implementation? I think we are good now, but no, not really. It works most of the time, but it still have a bug in it. So first, I want to talk about a concept called trivially relocatable. So the idea is trivially relocatable objects move can be implemented as relocate. So it's basically you can mem copy that object and then that's it. That's the whole move. And for most types, that's true. And currently we use move constructor, move assignment. It's overcomplicated. But not all the types can be implemented in this way. considering a node of a linked list, not I'm proposing you should use that ever, but if you have a node of linked list, you can consider some other node point to that node, and if you just do a mine copy, then you have dangled references. So that's why now we cannot rely on the previous behavior of just copy stuff as move. Instead, we need to do our move polymorphically, by adding another function pointer that will handle move for us. And this function pointer will just invoke the move constructor for us. Similarly, we need to dispatch on small, big. If it's small, then we invoke move constructor. If it's big, we just do the normal copy, the void stars. Another thing we need to change is this fit small function, meta function needs to check another condition, which is the move construction of our type cannot throw. Because if move construction can throw 1, this code will be totally broken because I defined my function pointer, move function pointer, where it is, as no except. 2, even though you never actually throw exception, no except will, if you call a maybe throw function in a no except function, then horrible thing code jam will happen. If you don't believe me, then try Godboard yourself. Also, so now we basically, the move operation will call that function pointer instead of directly doing exchange. Unique function version 5. So we don't need to store the whole vtable on the stack because currently our vtable is 3 function pointers, so it's 24 bytes. You can consider for some other types our vtable can even become bigger. And if we some days using 128-bit system, then it will become bigger, basically. So we don't want to store our vtable on the stack. The way to do it is first our behavior becomes singleton. And if you are a good OO programmer, the first reaction you hear singleton is probably not good. But I think in this case, it's OK because 1, behaviors don't have any initialization order problem. 2, it's const expert, so I don't think it's a problem.
Well, is it also unique per instantiation of the template?
Yeah. Yeah, exactly. That's why I make it singleton.
That's a lot of the problems.
What?
Oh, yeah, I was just saying, the const expert.
The const expert is this variable. This function is not const expert. It can't.
Yeah, I was just saying that the const expertness and then the fact that there's only 1 per template instantiation makes most of the problems go away because the functions should be the same.
Yeah. What? Now, for every different underlying function type, function object type, we basically have this kind of vtable, exactly like what happens when you're doing inheritance. And then we need to store this thing as a pointer instead of the stack directly, because it's in the static storage now. And we initialize by calling this get instance function, just like normal singleton do. When we invoke, we also need to first get the pointer and then invoke the actual function pointer. So it's two indirection instead of 1 with previous implementation. But I had some really unreliable benchmark, and I didn't see any differences. So I think that's good enough. And we have some other kind of mechanical change to basically change all the dots to arrows. Like this. All the dots to arrows, basically. So I have an implementation of unique function online, which is not this implementation, and I hope it's more robust and better tested than this implementation. I read this implementation for the slides, basically, for the talk. So our implementation of type erasure is really specific. If you want something more general, then there are libraries. But I want to warn you, when this kind of library is not idiomatic, as I said, intrusiveness do have some good part. So, but those are libraries and they can be useful. I only have experience with Dano before, so I cannot say about others. And Chris read this library, Boost TE, so if you should ask why this library is better than all of others. Also, don't use this Adobe Poly. That's from the Sean Parents. Sean Parents talk about that, but that library is too early, so it still uses reference semantics. So no SBO, no all the good stuff. And why not just use inheritance? Thank you. Yeah, questions?
So you mentioned this is a proposal. Where is it in the standard? Is it in ++20 or is it?
Unique function, you mean?
Yeah, unique function.
Not in 20.
Okay.
Yeah, but one of the idea I want to show is this kind of thing is not that hard to implement it. So, other questions? Yeah?
I have a question. One of your slides had a comment on it saying to do guard against self-assignment.
Well, I said I don't guard against self-assignment because I think it's just dumb to move an object to itself. Who writes this kind of code?
I used to think that, but there were some use cases that persuaded me the other way. I'm not sure what to think.
Yeah, well, in this implementation, I actually guarded against it.
Oh, I had a question as well. Since you
Yeah.
show some C++ 20 things in there, and we're looking at your boilerplate spin-A that's like 15 lines long to prevent being a move constructor. It seems like it should be possible to
Concept.
write a don't be a move constructor concept that we could just spin-A on. Did you look into that?
No, I have no idea. So.
You agree it seems like a concept to be able to handle that? I get a couple of nods. Okay. Someone should write a don't be a move constructor concept.
I think self-assignment also kind of going to have immediacy. So you have a reference to it.
Yeah.
It is assignment and another thing. You could actually, indirectly.
Yeah, I guess I just write in a style to minimize moves, so I don't see this problem will ever happen, but I guess it can.
Well,
What does the algorithm say?
yeah, the important use case is accumulate is one of them. The important use case I saw that is where you pass an R value to a function and you assign the result of that function back to what you passed. So you carry your result through.
Kind of like Rust borrow checking. Well, not checking, just Rust borrowing. Kind of. Yeah. Yeah?
So a lot of the things that you're using, like the template standard function, which version of C++ were those introduced in?
You mean what?
So like C++ 11, C++ 14, C++ 17.
So most type traits are implemented in 11, are introduced in 11, and I don't think I used any 17 feature in the slides. Maybe some, but they are easily circumventable.
You mentioned deduction guides.
Yeah. Yeah.
Yes.
Yeah, but yeah, they are circumventable, and deduction guides, if that's not a thing, just not a thing. And I use 120 feature, which is the designated initializer.